Hi, this is Dr. Srikat Majumdar. Today we will discuss applications of Bose-Einstein statistics. Already we have discussed the basic postulates of Bose-Einstein statistics, Bose-Einstein distribution law, and the Bose-Einstein distribution function. So the topic is applications of Bose-Einstein statistics. It falls under module 5, Statistical Mechanics. Learning objective is to compute macroscopic properties from the quantum mechanical information about the atoms and molecules of interest. Derivation of Planck's law of radiation from Bose-Einstein statistics. According to Planck's law, the amount of energy radiated per unit volume of a black body, that means the emissive energy density, energy emitted per unit volume, is the emissive energy density, in between the frequency range nu and nu plus d nu at absolute temperature T is given by E nu d nu is equal to 8 pi h nu cube by c cube 1 by e to the power h nu by kt minus 1 d nu. Here h is the Planck's constant, nu is the frequency of radiation, c is the velocity of light, k is the Boltzmann constant, and t is the temperature in Kelvin. This is the well known Planck's black body radiation law that is calculated from the purely statistical idea, and we have discussed it during the black body radiation law, and how it can be calculated, it is also discussed. So we have to find out the Planck's black body radiation law. E nu d nu is equal to 8 pi h nu cube by c cube into 1 by e to the power h nu by kt minus 1 d nu from the Bose-Einstein statistics. Now let us start from the Bose-Einstein statistics. In 1905, Einstein suggested that the electromagnetic radiations due to emission or absorption by a black body are composed of discrete energy particles called photons. We know the photons having energy 0, epsa means h nu, 2h nu, 3h nu, that means discrete packets of energy, either 0 or epsa, that means multiple of epsa, n starting from 0, 1, 2, 3 and so on. If n is equal to 0, then energy is 0. If n is equal to 1, then energy is h nu and so on. In 1924, Professor S.N. Bose, a scientist from Calcutta, formulated the new statistics to shoot the system of photons. The radiation inside an enclosure maintained at constant temperature, that means the enclosure is in thermal equilibrium, may be considered as photon gas. That means the radiation inside an enclosure maintained at constant temperature may be considered as photon gas. The walls of a black body can absorb or emit photons of different energies. These photons are indistinguishable and many photons can have same energy. The walls of a black body can absorb or emit photons of different energies. Already we have discussed, already we have stated, they are distinguishable and having same energy. The photons can interact only with the atoms of the walls of the cavity. Photons have integral spin and obey Bose-Einstein statistics. Already we have discussed the particles that are obeying Bose-Einstein statistics, that are the bosons, and photon is an example of boson, and all the bosons having integral spin and they do not obey Pauli's exclusion principle. Now come to the point how we can derive Planck's law from Bose-Einstein statistics. In black body radiation, photons of different energies are absorbed or emitted by the atoms of the walls of the enclosure. Thus, the total number of photons present in the enclosure is not constant. Therefore, Ni is equal to constant or dNi is equal to 0 is no longer valid. As n is not a constant, so dNi not is equal to 0. That means, so this is the basic concept. Ni is equal to constant and dNi is equal to derivative of Ni, dNi is 0, is no longer valid. Though the total energies remain constant. So what will happen? Alpha dNi is 0. Alpha dNi 0 means the multiplier alpha is equal to 0. As dNi not is equal to 0, so multiplier alpha will be 0. Now we know the Bose-Einstein distribution law is Ni is the number of particles, Gi is the number of quantum states. Ni is equal to Gi by e to the power alpha plus beta Ei minus 1. Now alpha is equal to 0 means this equation reduces to Ni, this part is 0, so Gi by e to the power beta Ei minus 1. So Ni is equal to Gi by e to the power beta Ei minus 1. Again we know the multiplier beta is equal to 1 by kT, where k is the Boltzmann constant and T is the absolute temperature in Kelvin scale. Thus we can write Ni is equal to Gi by e to the power beta means 1 by kT, so this becomes Ei by kT minus 1. Thus the number of photons, here it is bosons, in the frequency range nu and nu plus dnu is obtained by replacing Gi by gnu dnu and Ni by nu dnu. That means number of quantum states within the frequency range nu and nu plus dnu and number of particles within the frequency range nu and nu plus dnu. That means this equation Ni it will be changed by nu dnu and Gi will be changed by gnu dnu. So come to this point. Thus Ni is equal to Gi by e to the power Ei by kT minus 1 can be written as nu dnu. Gi becomes gnu dnu by e to the power h nu by kt minus 1. Here g nu d nu is the number of quantum states in the frequency range nu and nu plus d nu. If V be the volume of the bosons in phase space, that is the volume of the enclosure, the number of quantum states in between the momentum range P and P plus dP is, already we have calculated in our earlier lecture, this GPdP, number of quantum states in between the momentum range P and P plus dP, we are representing it as GPdP is equal to 2 into V by h cube 4 pi p square dP. Why this multiplication by 2? Basically, electrons having 2 allowed, electrons, protons, etc. having 2 allowed spin quantum states. Similarly, photon is also plus minus 1 h cut spin quantum states. So that means there are 2 allowed spin quantum states of each photon. So we are multiplying this by 2. So it becomes GPdP is equal to 8 pi V by h cube p square dP. The energy and frequency of a photon are related by E is equal to mc square. Einstein's equation E is equal to mc square. And the energy of photon is E is equal to h nu. So momentum of the photon is P is equal to h nu by c. On differentiation, we will get dP is equal to h by c d nu. Thus, the number of quantum states in between the frequency range nu and nu plus d nu, we are writing this GPdP, as g nu d nu. So we will change this p square dP with in terms of nu. So dP in terms of nu is h by c d nu, and p square means h nu by c whole square. So if we put this p square in terms of nu and dP in terms of d nu, then GPdP we will write it as g nu d nu. G nu d nu is equal to 8 pi V by h cube. We are replacing p square by h nu by c whole square and dP by h by c d nu. So this becomes 8 pi V by c square into 1 by c, that means c cube, into h cube, and this h square into 1h means h cube will cancel out. So this one becomes 8 pi V by c cube nu square d nu. The number of photons or bosons in the frequency range nu and nu plus d nu is obtained by replacing the value of g nu d nu. So n nu d nu is equal to 8 pi V. This formula was n nu d nu is equal to g nu d nu by e to the power h nu by kt minus 1. Now we are replacing g nu d nu by this 8 pi V by c cube nu square d nu. So it becomes n nu d nu is equal to, in place of g nu d nu we are writing this 8 pi V by c cube nu square d nu into 1 by e to the power h nu by kt minus 1. The amount of energy per unit volume of the enclosure, that is the energy density or radiation within the frequency range nu and nu plus d nu, is given by nu d nu be the number of particles within the frequency range nu and nu plus d nu. Each particles having energy h nu, so total energy becomes h nu into n nu d nu. So per unit volume means divided by V. So this becomes energy density within the frequency range nu and nu plus d nu. So this is nu d nu is equal to h nu into n nu d nu by V. So we are segregating h nu by V into n nu d nu means previously we have just calculated 8 pi V by c cube nu square d nu 1 by to the power h nu by kt minus 1. So putting it here 8 pi V by c cube nu square d nu by to the power h nu by kt minus 1. Now this V and this V will cancel out. So it becomes, the equation becomes 8 pi h, this one is nu, another one nu square is here. So it becomes 8 pi h nu cube by c cube 1 by e to the power h nu by kt minus 1 d nu. This is the Planck's blackbody radiation law in terms of frequency nu. Now we can find it out in terms of wavelength lambda also. Planck's blackbody radiation law in terms of wavelength range lambda and lambda plus d lambda by putting nu is equal to c by lambda. So d nu becomes minus c by lambda square d lambda. So difference means difference of this frequency d nu is equal to mod of minus c by lambda square d lambda. So putting it here, e lambda d lambda is equal to 8 pi h by c cube, nu cube means c by lambda whole cube into 1 by e to the power h nu means c by lambda is c by lambda kt minus 1, d nu means minus c by lambda square d lambda. So putting this mod form, so it becomes 8 pi hc by lambda to the power 5 1 by e to the power hc by lambda kt minus 1 d lambda. So this part is lambda to the power 5 means how it comes, nu cube means c cube by lambda cube. So c cube and c cube will cancel out, lambda cube at the denominator part, again we will get from d nu minus c by lambda square. For taking mod there will be no minus, so c by lambda square means, so lambda to the power in the denominator part, one is lambda to the power 3, another one is lambda to the power 2, so it becomes lambda to the power 5. So this c cube is nu cube c cube, it will cancel out. So this nu means c by lambda c cube, so only one c will exist. So 8 pi hc by lambda to the power 5 1 by e to the power hc by lambda kt minus 1 d lambda. This is already we have discussed during in the blackbody radiation lecture video. Now the classical limit of quantum statistics. The distribution functions of MB, BE and FD statistics are respectively given below. So Maxwell-Boltzmann distribution function, if we write it as FEI MB is equal to Ni by Gi is the occupation index. That means distribution function is like this, is equal to 1 by e to the power alpha plus beta EI. This alpha and beta are the multipliers. For Bose-Einstein, FEI BE is equal to Ni by Gi 1 by e to the power alpha plus beta EI minus 1. And for Fermi-Dirac statistics, FEI FD is equal to Ni by Gi is equal to 1 by e to the power alpha plus beta ei plus 1. So in all the above cases, beta is equal to 1 by kt. As alpha and beta are the multipliers, beta is equal to 1 by kt. Now we can represent the distribution functions for all the three statistics as Fe is equal to Ni by Gi is equal to 1 by e to the power alpha plus beta ei. So we can write plus delta. Alpha plus beta ei, put in the value of beta is 1 by kt. As it is plus, we can write in the exponential form as e to the power alpha into e to the power ei by kt plus delta. Now delta is equal to 0 means it becomes e to the power alpha plus beta ei. It is a Maxwell-Boltzmann statistics. When delta is equal to plus 1, then Fe becomes 1 by e to the power alpha plus beta ei plus 1. This is the Fermat statistics. When delta is equal to minus 1, Fei becomes 1 by e to the power alpha plus e to the power beta ei minus 1. This is the Bose-Einstein statistics. So depending upon delta 0, putting the value of delta 0 into this equation, it is a Maxwell-Boltzmann statistics or Maxwell-Boltzmann distribution function. Delta is equal to minus 1, it is a Bose-Einstein distribution function. Delta is equal to plus 1, it is a Fermat distribution function. Now if we plot, already we have discussed this one in our previous lecture. So again we are depicting this in pictorial form. If we represent distribution function, three distribution functions in terms of alpha plus beta ei, so Fermat statistics having the lowest slope, Maxwell-Boltzmann in between its slope is in between B and FD. At a higher energy, all these three statistics B, MB and MD at the higher energy level coincides at the same point. So again in our next slides we will discuss how this quantum statistics reduces to the classical statistics at higher temperature and low particle density. It is obvious that the quantum statistics BE and FD would tend to the classical one. Classical statistics means MB statistics only when e to the power alpha into e to the power ei by kt very greater than 1. Come to this formula. If delta is equal to 0, then it is Maxwell-Boltzmann. Delta is equal to minus 1, it is B. Delta is plus 1, it is FD. Now, if this term e to the power alpha plus beta ei is very greater than this delta, whatever is the value of delta, is very greater than delta, then only this term will survive. So when delta is equal to 1, so if e to the power alpha plus beta ei is very greater than 1, then what will happen? This term only we can write, only this term will exist, e to the power alpha plus beta ei, or in the multiplicative form e to the power alpha into e to the power ei by kt. This will only exist. So If this term is greater than 1, then Ni by Gi will be very less than 1. As this one is very greater than 1, so moving up, it becomes e to the power minus alpha into e to the power minus Ei by Kt. So this Ni by Gi will be very less than 1. Now the parameter alpha for both BE and FD statistics is inversely proportional to T. We know alpha is equal to minus EF by KT for FD statistics, and for B statistics alpha is equal to minus mu by KT. Mu is the chemical potential and EF is the Fermi energy. So the parameter alpha is inversely proportional to T for both BE and FD statistics. Thus, if very high value of the temperature T corresponding to the very low value of Ni by Gi, that means temperature T more means Ni by Gi is very small. The quantum statistics reduces to the classical one. Here Ni by Gi is the number of particles per unit state. Number of particles Ni, Gi is a state, so per unit state, and can be treated as particle density. Hence, this Ni by Gi is very less than 1. So, under high temperature and low particle density, the quantum statistics tend to classical one.